Okay, hi. I made this video, or I'm making this video, um, to go over study goals 11 and 14. These are for assignment 6.1, which I was hoping to finish today. And I want to remind you, I put these videos on YouTube so that you can pause, study, take notes, and so on. We've spent a couple days already talking about this one assignment. And I left these two study goals for the end because I think that these might have a little bit more nitty gritty, perhaps more stuff to take notes on. And so I want to make sure that you're using our class time as well as we can. I want to give you a heads up. The course definitely gets a little bit more detailed, so please keep that in mind. Okay, for study goal number 11, I want to distinguish first law and second law efficiency, which are based on the first and the second laws of thermodynamics. We've talked about these a lot. Energy is neither made nor lost, it just changes form. And when energy changes, some quality is lost. You'll notice that the first law of thermodynamics is about the amount of energy. So the amount doesn't change. It's not made, it's not lost. Some people call it the constancy of energy law because the amount is constant. And so when you discuss efficiency in terms of amount, like the ratio of input from output, you're talking about the amount. This is the type of efficiency that everybody talks about, miles per gallon, the amount of output your car gives you from the amount of input you put into your car, miles per gallon. And this is the common one. It's easy. When people talk efficiency, it is assumed that they're saying first law efficiency. But I'd like you to consider something new now, the second law efficiency. Second law of thermodynamics is about quality. So during a change of energy forms, some quality will be lost. And I'd like you to consider how the quality of an output could match the quality of the input. There's really no examples because this is something that we never talk about, but it is actually really important. Imagine in our homes, we use natural gas, which burns at like 2000 degrees or something, to heat up the air that we pump into our house to raise the temperature of our house by a couple of degrees. We're using really high quality input, right? Natural gas is a high quality input. We're using a high quality input to generate a really low quality output. We're just like 2 degrees, like you could just put on a sweatshirt and then it doesn't matter. This is squandering high quality energy, which is hard to find, for low quality outputs. You could chase your dog in a circle in a well-insulated living room, and the amount of body heat coming off you and the dog would be enough to raise the temperature of a well-insulated living room. It's actually a famous experiment. Imagine that you were wiping your nose with $100 bills. Somebody walked by and go, "Bro, what are you doing? What are you doing? You could just use a Kleenex." And you're like, "Yeah, whatever. I'm just using $100 bills because I got them." And all over the world, people probably think that that's what most wealthy people are doing when we have exceptionally valuable, high quality energy that we're wasting just to raise the temperature of our house a little bit. So first law efficiency about the amount, second law efficiency about the quality of energy. Remember that high quality fuels are hard to get. You should save that. Like if you need to melt sand into glass, you can't chase a dog to build that amount of heat. If you need to cook an egg, Natural gas will get it done pretty quick. You can't really chase your dog to cook an egg. So when you just need to raise the temperature a couple of degrees, maybe we shouldn't be using, nuclear power or whatever for something like that. Second law of efficiency. Okay. The next study goal that I wanted to talk about, and the last one left in assignment 6.1, I think, is about how we can save energy. In the United States, we've got three major priorities. Maybe you remember them. If you look here, this one you did, right? I think you did this one. If you look here, about 2/3 of the energy potential that goes into electricity, about 2/3 is lost. Only 1/3 of our energy potential is delivered as electricity. And look at cars. Oh my God, we put that amount of units into it, 27.1, to get just 5 or 6 units out of that. That's like an 80% waste right there. And then, a place where most of us could probably save a little bit is in our homes. That's like a 60-40 split. So about 60% is useful, about 40% is wasted, give or take. So those are the big wastes. Keep in mind that we're doing all of these major investments in pollution and climate change and wars and holes in the ground, and we're wasting our surface waters to get all this energy. And it would be cool if we could get more delivered usability from that energy, given that right now about 60% of America's energy potential is lost. So how do we fix that? Number 1, transportation. Number 2, the grid. Number 3, our homes. And I'll give you little lectures about each of those sections. Number 1, transportation. This is probably our biggest loss overall. You can see here about 80%. And electricity, about 2/3 lost. Homes are third, less. I'll explain each of these. So transportation efficiency is really simple. The first car to get 100 miles per gallon was not a Prius. The first car to get 100 miles per gallon was made way before you were born. I believe that this is even before my brother was born. This is a long time ago. 1983 is a long, long time ago. And the first car to get 100 miles per gallon was nothing that fancy. It was called the Volvo LCP 2000. You should look it up. It's a dorky looking car. It looks like a dart. It just had like a small diesel engine, and the car was crazy light. And that's all. We've been able to make efficient cars forever, but nobody wants efficient cars. We don't need to wait for new technology. We need to convince people to use old technology. We've had efficient cars for a really long time, but everybody wants a bigger car, faster car that you can put more chicks and kegs into and then blast your music and then power them and put it jacked up on big old tires because you've got small hands or whatever. The first mass-produced car had a fuel efficiency of 13 miles per gallon. On the 100-year anniversary of that car, Ford's fleet average was 13 miles per gallon, the exact same as when they started mass-producing cars. Those cars became way safer, thank God. Those cars became way faster, thank God. Those cars became way more comfortable. They have more cup holders, thank God. But we only really care about fuel efficiency when gas prices spike. And as long as people can keep turning up the dial and turning down the dial on gasoline prices, which they can, we don't really seem to care too much. You can track like the highlights of hybrid vehicles or of efficient vehicles were precisely when gasoline got expensive. So all the way back to like the 1970s, there was like a conflict between Iraq and Iran that affected the global supply of petroleum. Volvo made that LCP 2000, this car from 1983, they made that in response to an oil shortage. By the time it was developed, the oil shortage had passed and nobody bought the car. They made 3. Nobody really wants efficient cars. And so I told you before, we should all drive slower. We should have lighter vehicles. We shouldn't drive as much, you especially, because you're murder machines. But I don't know. It just feels like transportation is too, I don't know. I don't feel like that's going to change. I'm not trying to be a jerk. You know, we've kind of painted ourselves into a pattern with the way our country's designed, the amount of driving we do and stuff, our cities and our business areas and where we live in the suburb model. And, you know, like the car you buy is like an expression of your personhood. And so I don't really know how to change people's transportation choices. The technology is already there. Okay. Number 2 is the grid. Remember, if you start with 100 units, we lose 1/3 in generation, and of what goes onto the wires, we lose 1/2. So 1/3 of the energy potential is delivered, right? Because you cut 1/3 when you're making the electricity, and then of electricity, you lose 1/2 in transmission. So today we're only delivering about 1/3 of our energy potential to electricity as consumers, and that's huge. That's the second biggest waste of energy in the United States. And so we could improve generation, but you're always going to lose some, right? Whenever you change energy forms from one to another, you're going to lose some as a quality drop. You're going to make some heat. So when you're going to take anything and make electricity, you're going to make some heat. There's going to be some loss. But it's probably worth mentioning that you really can't do worse than coal. Coal is just simple. So globally, when anybody's starting an electrical grid, they've got to start with coal because it's simple. Engineering-wise, mechanically, coal is simple, but coal is by far the worst. Any nation like the United States quickly transitions out of coal because it's just the worst. You put all this effort into moving really heavy fuel, really long distances to use crappy old power plants that give off a ton of heat. And by the way, they give off a ton of pollution. So as soon as you start worrying about your pollution, there's just like coal's got to lose. And we're going to talk about alternative energy later in this unit. I do want to talk now, though, about transmission. In terms of the grid, in the United States, we have a lot of room to grow. Right now, we have a huge electricity grid because our country's really big. It's really, really old. Thomas Edison wrote the plans for the basic backbone that we're still using throughout the United States. It's also important to point out that we get our energy far from where we live. So in a big country like ours, there's like places that have what we need, and then there's places where we are. So we're moving electricity really far. I'd like everybody to please visualize the grid, you know, like at a stadium where like people go like this and then they go like this. And I want you to remember, every time you've seen that happen, there's like somebody who doesn't know what they're doing, right? So everybody comes by and then some guy's like, oh, wait, and they like miss the timing, right? Or there will be somebody who's like on their cell phone. So then like you'll see like the grid come by and somebody's just like not doing it. And some like grumpy person that's like, I'm too cold, I'm not gonna get up. So as the excitement passes through the stadium, there's little errors. But now I want you to imagine that when a stadium is doing the wave, I hope everybody knows what I'm talking about when I say the wave, that when a stadium is doing the wave, imagine that every person will only stand up if the person beside them did. So when I'm on my phone, the wave dies with me, and all these guys are like, oh, Jose blew it, and then they don't stand up. That's how electricity works when you push it through a wire. Now I got to explain electricity, and then we'll come back to resistance. I'm sorry, this is vocab. We always talk about electricity as traveling electrons, but it isn't. It's electron excitement. This is really easy to do when we're in the classroom, I'm sorry. Electricity is not traveling electrons. You should probably write this down. Electricity is electron excitement being passed by atoms one to the next. So you've heard about the Bohr atomic model, where electrons are moving around an atom. That nucleus is kind of at the middle, and there's electrons flying around, the Bohr atomic model. And when you give that atom some energy, one of those electrons will boop, pop to a higher energy level. And then when gravity pulls that electron back to the nucleus, it will pass its excitement to the neighboring atom. That's electricity. So one atom is excited, its electron jumps a level. When the electron comes back down a level, that excitement is passed to the neighboring neighboring atom. So what you get is like a wave, where you've got a whole bunch of atoms next to each other, and this one gets a little bit excited, the electron comes back to the atom, this atom passes its excitement to the neighboring atom, whose electron jumps up a level, and then when that electron comes back to the atom, it passes its excitement to the neighboring atom, and this is electricity, where the excitement of an electron is transferred among neighboring atoms. And so when you give excitement over here, it will travel along a wire to neighboring atoms. That's electricity. It's electron excitement traveling among neighboring atoms. And like a wave in a stadium, once you get the party started, that excitement can be conducted among neighboring atoms. But I want you to remember that the one difference is when somebody blows it on the transfer of electricity, let's say that this one stops, now the neighboring atoms have lost that excitement. Point is that wires are imperfect. Electricity does not travel very well through wires. You may have heard of superconductors. They're really organized atoms, so that the excitement you give a superconductor will hopefully come out exactly the same at the other end. That's a superconductor. They transfer excitement really well. But wires don't. Wires are bad at transferring excitement. Wires resist. And so along the way, they lose electricity. Some of the electron excitement is interrupted. You know, like if you were doing the wave at a stadium, but a bunch of people were distracted, not very much would reach the other side of the stadium. Electricity dies in wires. It's called electrical resistivity. The idea that those atoms don't transfer excitement perfectly well. So moving electricity a long distance is really stupid, especially if your wires are old. We have a really big country with a really old grid. So I know that was a lot of vocab, but back to number 14, we could use alternative energy. So we're not so worried about fuels running out, and we're not so worried about pollution. We'll talk about that soon. And we could fix up our grid so that instead of transferring electricity long distances over old wires, we could maybe make really small amounts of energy really close to our homes. This is called micropower or microgeneration. You're producing energy at really small scale, just for like an individual house, or maybe for like a neighborhood, maybe like a small town. So then you're not wasting any in transmission, you're just making it for yourself or making it for your neighbor. Maybe it travels a couple of blocks. You don't lose as much. Hopefully these are alternative energy sources, so you're not making CO2. And you've probably seen stuff like this. So you could heat your water without natural gas by putting these on the roof. You see them all the time. Hippies used to build them out of bricks and stuff, but like car washes use them a lot. People use it to preheat the water for the jacuzzi. Keep in mind, these are water heater panels. These are photovoltaic, excuse me. These are photovoltaic panels. This makes electricity. You've probably seen these too. You can put them over a parking lot to charge electrical cars. You can put them on your roof to give electricity to your house. We'll talk more about these later. Keep in mind, you can make these really, really small if you want. So you don't need wires. If there's like one of those speed check trailers next to the road, it just makes the little bit of electricity that they need for the stupid sign that says how fast you're going. Wind can be done in really small scales. You can put a couple of wind turbines between the fence line of two farms. Since you can't grow along the fence, there's laws about that. Since you can't grow along the fence, why not put a couple of wind turbines, and now your farming community has independent micro generation of electricity. You know, will remind me about this when we talk about dams, but big dams are going out of fashion. They really do mess up rivers. But you could do micro power hydroelectric, like this, where you just trap a little bit of water, let it spill through a turbine to make electricity. Or like this, where you just divert a teeny percentage of the river to spin a big auger that cranks a generator. And another way to make micropower is to use biomass where it's available. So maybe you've got wood in your community, or maybe you've got paper trash, or maybe you've got fuels that you can make into alcohol, or leftover crops that you can make into alcohol, or maybe you've got some sort of gas. Biomass is another type of micropower. And in the US, we've probably got 3 separate places where we'll be talking about biomass. So I'd like you to write these down. You've already heard about ethanol, which is alcohol that you add to gasoline. Remember that currently we're making it from corn, which is stupid because that is carbon positive. But soon we'll be using agricultural waste, which would be carbon negative. That would be smart. Something else that you have not heard of, and we will talk about this later, but I'd like you to write it down now, is called digestion, where decomposers break up carbon bonds. And when you break up carbon bonds, anaerobic decomposers give off methane. You're going to need all those words, so I'll say them again. Digestion is decomposing carbon bonds. Anaerobically, that means without oxygen. Anaerobically, it's on the screen, anaerobic, which gives off methane, which is natural gas. And by the way, that's what happens in your gut. Inside your gut, you're digesting carbon bonds without oxygen, because after your stomach, there's no more oxygen. So in your intestines, there's no oxygen. And so when you break up carbon bonds without oxygen, you give off methane, which is why you can light your farts. You can do this in landfills. You can do this in wastewater treatment facilities. Digestion is a way that we can use biomass to generate energy in the United States. And of course, there's places that have firewood. If you've got a lot of trees, you might as well do something when they fall down in the road. There's a cutting edge market in taking sawdust and packing it into little pellets for pellet stoves. Turns out that that's like a huge energy potential locally. All right, so anyway, biomass is another type. And the big idea here is to find alternative fuel nearby so you don't have to transfer electricity very far. And yes, this does get super political. It's difficult, it's slow. I don't want to suggest that we just wave a hat or have a single election and this happens. But I would like to show you some fascinating research. Almost anywhere you are in the United States, you've got at least 2 sources of alternative micropower nearby. Anywhere you are. In the United States, you've got 2 sources of alternative micropower nearby. Kind of a shocking idea. But in many parts of the northern states, we've got an abundance of biomass. And then in the southern states, we've got an abundance of solar potential. And then in the middle states, we've got an abundance of wind. And I didn't get you a slide, but in the mountain states, we've got an abundance of small streams that we could use to make small amounts of electricity. And the point is, we don't need this big old grid powered by coal. We just don't. It's what we're doing. It's not smart. We don't need the other inputs. And, you know, at some point, we will be using really low quality, leftover, renewable sources of input to make electricity for our homes and our businesses. This is just a business opportunity that coincidentally has massive environmental benefits. I don't need to politicize this. It's a no-brainer. Remember that we were looking for 3 things, and third is our homes. Yeah, right, but we could make them smaller. We live in by far the largest houses on the world, and we live in houses twice the size of the same family size that our grandparents used. So every time you go to your grandma and grandpa's house, their home is half the size of what your home will be when you're their age. You know, if current trends continue. We kind of got crazy with these like mass-produced McMansions, mega houses, and that turned out to be pretty stupid. So we could make them smaller, we could insulate them better, and we could design them smarter. This is all about second law efficiency. So we could heat the house and cool the house and light the house without starting at fossil fuels. And this is called passive solar design. Back when we were in the class, you would do a giant year-long project on this, but we cannot. So this is all the lesson you'll get on it. Number 14. Third option, improving our homes, passive solar design. Imagine using sunlight to provide your lighting so you don't need as much electricity. Imagine using thermal mass so that once you heat up the walls and the floor, they stay hot overnight. Carefully arranging where you put eaves and awnings so that the sunlight is useful to you when it's cold, but it's blocked when it's hot. Smart ventilation, specific paints and materials, you know, like Adobe construction. This goes back to like when people lived in caves and stuff. It's just a good idea to have thermal mass, stuff that stays cool once it's cool or stays warm once it's warm. And most people kind of like natural lighting and stuff. So passive solar is using less traditional energy sources in our homes, less heating energy, less cooling energy, and less light. It costs more up front, but because energy is so expensive, you end up saving money in the long run. People buy really cheap houses and then they end up spending more to live there because they got to keep heating them or cooling them or lighting them. All right. I should probably stop. That was just a couple study goals, but a lot of notes. I'll see you after this. Make sure that you wrote down your questions. We'll talk soon. All right. Goodbye, children.